Welcome to the Deep Dive. Today we're looking into a really interesting paper called Sleep Time Compute, Beyond Inference Scaling at Test Time.
Yeah, it tackles a big headache with large language models.
Right. You want better performance on tricky reasoning tasks, so you scale up compute at test time.
But then, bam, you're hit with huge latency, like minutes per query, and the costs can rack up sometimes tens of dollars.
And a lot of that comes from treating related queries as totally separate, making the model redo work.
Exactly, the stateless assumption. This paper flips that with something they call sleep time compute.
Okay, sleep time compute. So the model kind of thinks ahead while it's idle.
Pretty much, it processes the context before you even ask a question, anticipating what might be useful.
Like a coding assistant figuring out potential bugs before I ask it to debug.
That's a great analogy. And the payoff looks promising. They're reporting roughly a 5x cut in test time compute needed for the same accuracy on some reasoning tasks.
5 times. Wow. And that's not all, right?
Nope. If you invest more in that sleep time phase, accuracy can climb even higher. They saw gains up to 18% on one benchmark.
And it helps with costs if you ask follow-up questions.
Definitely. By reusing the pre-computed stuff, they cut the average cost per query by about 2.5 times when asking multiple related questions.
Okay, and it works best when the questions are kind of predictable.
That's what they found. If the context gives good clues about what might be asked, sleep time compute shines. They even showed this in a software engineering case study.
Super interesting. All right, let's dig into the details of how this all works.
Sounds good. So the core issue, as we touched on, is this statelessness assumption in standard test time inference.
Yeah, explain that a bit more. Why is it such a problem?
Well, think about practical applications. Document Q&A, coding agents, even just chatbots having a conversation, the context sticks around, right?
Sure, you're asking questions about the same document or the same code base.
Exactly. But the standard approach often forces the model to reread and reprocess that whole context for every single query, even if it's closely related to the last one.
That sounds incredibly inefficient, like rereading a whole chapter just to answer a question about the last paragraph you discussed.
Precisely. It's computationally redundant. This paper argues, quite convincingly, I think, that we need to move beyond that for these stateful applications.
Okay, so sleep time compute is the proposed solution. How does it actually work under the hood?
The idea is to use the time the model is idle between user interactions to do useful work.
So instead of just waiting.
It proactively processes the current context. The paper talks about prompting the model to generate a new representation of the original context. Let's say the original is C.
All right.
The model creates a C prime. The C prime isn't just the original context. It includes inferences, summaries, potential connections, things the model anticipates might be useful for future questions, Q.
Ah, so it's doing some thinking, some pre-computation based on C.
Exactly. Preemptive reasoning, if you like.
And then when I, the user, actually ask my question queue, what happens? What's the benefit?
The big win is at test time. Instead of feeding the model the original, potentially large context C along with your query Q.
You give it the pre-processed C prime.
You got it. And because C prime already contains relevant computed information, the model needs much less new computation at test time to figure out the answer.
So less work when I'm actually waiting for the answer.
Right. The paper uses the notation TBQC versus the standard TBQC. That test time budget B for the sleep time approach is much smaller than the budget B needed for the standard way.
Which means faster responses, lower latency.
Lower latency and also lower test time computational cost.
And you mentioned reusing the C prime. How does that work?
That's key for cost savings in conversations or multi-query scenarios. Since C prime is derived from the original C, it's relevant to any query about C.
So if I ask 3 questions about the same document,
you do the sleep time compute once to generate C prime, and then you use that same C prime to answer all 3 questions, each time using only a small amount of test time compute.
Okay, so that initial investment in sleep time compute gets spread out, amortized.
Precisely. Which can drastically lower the average cost per query compared to the standard stateless approach where each query starts from scratch.
Makes sense. Now, to prove this works, they couldn't just use standard benchmarks, could they? They needed something stateful.
That's a really important point. Most benchmarks are just question-answer pairs in isolation. They don't capture this idea of a persistent context.
So what do they do?
They got creative. They took existing math reasoning benchmarks, GSM Symbolic and AIM, which are known to be pretty tough,
Okay.
and they split each problem Part of it became the context, and the other part became the question. This created their stateful versions.
Ah, so mimicking that setup of having some background info and then asking something specific about it.
Exactly. For stateful GSM Symbolic, they ended up with thousands of examples, 5,000 for the easier P1 split, 2,500 for the harder P2. For the really complex AMI problems, they created 60 stateful examples.
The paper has an example, right? Figure 2.
Yeah, it shows a GSM Symbolic problem about a juggler's balls. The description becomes the context, and the question about, say, indigo tennis balls becomes the query. A neat illustration.
Okay, that covers single follow-up questions. But what about the amortization part, the multiple queries?
For that, they built another dataset, multi-query GSM Symbolic.
How did they make that one?
They took each context from stateful GSM Symbolic and used another language model, O3 Mini, to generate multiple related questions for that same context.
So one piece of background info, but several different things you could ask about it.
Right. Figure 1 shows this flow raw context, then the sleep time processing creates a learned context, and then multiple different queries can potentially use that shared learned context.
Got it. And they detail the stats for this multi-query dataset too.
Yep. Table 1 breaks down the number of contexts, original questions, and newly generated questions for both GSM Symbolic P1 and P2.
Okay, datasets sorted. Which models did they actually run these experiments on?
They chose models strategically. Models that aren't great with very little test time compute, but improve a lot when you give them more.
Makes sense. You want to see if sleep time compute can help bridge that gap.
Exactly. For GSM Symbolic, they used GPT-4o Mini and the full GPT-4o. For the harder AIM tasks, they used a wider set. OpenAI's O1 and O3 Mini, Anthropic's Claude Sonnet 3.7 Extended Thinking, and DeepSeek R1.
A good range.
Yeah.
And the baseline they compared against was just the standard way. Context and query together at test time.
That was the main baseline, yeah. Standard test time compute.
Did they have any other controls?
They did include a context-only baseline, which is interesting. They basically gave the model just the context and asked it to guess the question and answer it.
Why do that?
To make sure the questions weren't too obvious from the context. If the model could answer well without even seeing the real question, then the stateful setup wouldn't be truly testing the approach.
Oh, okay. A sanity check.
Right. And sleep time compute significantly beat that baseline, showing the model really did need the specific query. Those details are in the appendix, figures 21 and 22.
Okay, let's get to the results. The paper talks about Pareto Improvement. What does that mean for us?
So think of a graph where one axis is test time compute cost and the other is accuracy. The Pareto frontier is like the edge of achievable performance.
The best accuracy you can get for a given cost.
Exactly. A Pareto improvement means the sleep time compute method shifts that whole frontier outwards and upwards.
So for the same cost, you get better accuracy.
Or for the same accuracy, you need less cost specifically, less test time compute. Figure 3 shows this for stateful GSM Symbolic. They found they could get similar accuracy with about 5 times less test time compute using sleep time, especially at the lower budget end.
5 times less compute is huge. Did it always outperform?
Interestingly, no. At the very high end of test time budgets, the standard baseline sometimes did slightly better.
Huh. Why?
Their guess is that the pre-processed context and sleep time might contain extra inferred information that could act as a slight distraction when the model already has ample compute to focus solely on the query and the most relevant parts of the original context.
Okay, that's a subtle point.
Yeah.
What about the harder AIM dataset? Similar results?
Broadly, yes. Figure 4 shows the AIM results. For most models, O3 Mini, Claude Sonnet, DeepSeek R1, there was a clear Pareto shift. Sleep time compute let them reach similar performance levels, but using much less test time compute.
Any exceptions?
The O1 model didn't seem to benefit as much, showing only limited gains.
Okay. Now, they also compared this to another scaling method, Passat K. What is that?
Passat K is about generating multiple answers, say K answers, in parallel at test time. The hope is at least one of them will be right.
Kind of like throwing darts hoping one hits the bullseye.
Sort of. But the big catch with Passat K is assuming you have a perfect way, an oracle, to know which of the K answers is the correct one.
Which you usually don't have in the real world.
Right. A perfect verifier is often unrealistic or costly itself. So they compared sleep time compute against Passat K using the same total test time token budget.
And how did sleep time compute do?
It consistently came out ahead. Figures 5 and 6 show this across the different tasks and models. It seems to be a more efficient way to use inference compute without needing that magic verifier.
Good to know. So sleep time compute works. What if you throw more resources at the sleep part? Can you make it even better?
That's a key question. They investigated scaling sleep time compute itself.
How do they scale it?
Couple of ways. For models like GPT, they tried generating multiple different pre-processed contexts in parallel during sleep time. For others, they varied the amount of reasoning effort the model put in during sleep time.
And did putting more work in upfront pay off?
It did. Figure 7, for stateful GSM Symbolic, shows further Pareto improvements. Scaling sleep time compute pushed accuracy higher by up to 13% in some cases, especially for the harder problems and the better models like GPT-4o.
13% is a solid gain. Any limits?
Yeah, they did see diminishing returns. After a certain point, adding more parallel agents or reasoning effort didn't help much more, so there's likely an optimal amount of sleep compute.
And for AIM?
Similar story. Figure 8 and another one in the appendix show the same kind of outward shift in the Pareto curve. Performance improved by up to 18% by scaling up sleep time compute.
Wow, 18%. That's significant. Okay, let's swing back to the cost saving for multiple queries and the amortization.
Yeah.
How did they measure that cost?
Right, the idea is simple. Do the heavy lifting once during sleep, reuse it for many queries. To quantify the cost, they made a reasonable assumption. Test time compute is more critical for user experience, so latency matters more.
So they weighted test time tokens higher.
Yeah, they set test time tokens as 10 times more costly than sleep time tokens in their model.
Makes practical sense. And using the multi-query GSM symbolic dataset, what did they find?
Figure 9 shows the results. It was pretty dramatic. With 10 related queries per context, the average cost per query dropped by up to 2.5 times compared to the baseline of handling each query independently.
2.5 times cheaper on average. That could make a lot of conversational AI applications much more viable.
Absolutely. It highlights the economic benefit for stateful interactions.
Now, they also looked at when sleep time compute is most effective. Something about query predictability.
Yes, they hypothesized it would work best if the questions are somewhat predictable from the context. If the model can guess what kinds of things might be asked, its sleep time preparation can be more targeted.
How did they measure predictability?
They used another LLM, Llama 270B, to calculate the probability of the question arising given the context. High probability meant more predictable.
Okay. And did the results back up the hypothesis?
They did. Figure 10 shows the accuracy gap between sleep time compute and the standard baseline. That gap got wider as question predictability increased.
So the more predictable the question, the bigger the advantage for sleep time compute.
Exactly. Which intuitively makes sense if you have a good idea what's coming, preparing for it is much more effective.
Okay, finally, they didn't just stick to math problems. They tried this on a software engineering task.
Right, a case study to show real-world applicability. They used a benchmark they developed called SWE features.
SWE features. What's different about that?
It focuses on implementing new features in code bases, tasks that typically require changing multiple files, at least 3, in their setup. This is more complex than benchmarks focusing on small bug fixes in single files.
So a more realistic, chunkier software task. Where did they get the data?
They collected pull requests from actual open source projects like Aider AI and Comfy UI, about 33 examples in total.
And how did they test sleep time compute here?
They used an agent based on Claude Sonnet 3.7. With sleep time compute, the agent got to look at related, relevant pull requests before tackling the main feature request.
How did it know which PRs were relevant?
They used some clustering techniques based on PR content to find similar past tasks. That's detailed in Appendix D.
Okay, so it got some relevant context beforehand, and the baseline.
The baseline agent only got that related PR info at test time when it was already working on the main tasks.
Got it. How do they measure success?
They used the F1 score, comparing the files the agent thought it needed to change versus the files that actually were changed in the real pull request.
And the results. Did sleep time help the coding agent?
Figure 11 shows it did, especially at lower test time budgets. Sleep time compute achieved a higher F1 score, getting similar performance with about 1.5 times fewer test time tokens.
So again, efficiency gains at lower budgets.
Yes. But interestingly, similar to the math tasks, at very high test time budgets, the standard approach actually pulled slightly ahead.
Any idea why?
The hypothesis is maybe the standard approach allowed the agent to focus more narrowly on fewer files earlier when given tons of compute, whereas the sleep time agent might have considered a broader set initially based on the pre-analysis.
Interesting trade-offs there. Okay, let's wrap this up. For the AI researchers and ML engineers listening, what are the big takeaways from this sleep time compute paper?
I think the main takeaway is that it offers a really promising alternative to just brute forcing test time compute, especially for stateful apps.
Right. Anywhere context persists or where you might expect related follow-up questions.
Exactly. And especially if those follow-up questions have some predictability based on the initial context, it shows you can potentially cut test time compute and latency significantly.
We saw that 5x reduction figure. And it's not just about saving compute, right? Scaling the sleep time part itself can actually boost accuracy.
Yeah, those 13% and 18% accuracy gains on GSM Symbolic and AIM by scaling sleep time compute were quite impressive. And the cost amortization, that 2.5x reduction in average cost for multi-query scenarios, is also a huge deal.
Plus the insight about query predictability, helping to guide where this technique might be most impactful.
Definitely. And the SSWE features case study grounds it in a complex real-world domain.
So the final thought for our listeners, maybe think about your own workflows. Are you dealing with persistent contexts, or could you anticipate user interactions?
Could you identify patterns where some offline proactive computation, some sleep time for your models, could make your system faster, cheaper, or even more accurate when the actual interaction happens?
It's a different way to think about scaling inference. We definitely recommend reading the full paper and checking out their code and data. The GitHub link is in the description.
Lots to think about there.
Absolutely. Thanks for joining us for this deep dive.